So let me introduce Vlad Kostylev, a former colleague of mine at the Geological Survey of Canada. And Vlad came to BIO at a time when we had the sea mapping program came out of the Oceans Act and the Oceans Action Plan and things like that, and did some really innovative things in terms of using multibeam data for habitat mapping. And so he's going to cast his mind back a few years and treat us to some of the past and present pieces of work that they're doing. So Vlad,
that's right. Okay,
there you go.
This goes here. Okay,
I'll put it right there, I think. Oops, sorry. Okay.
Yeah, I'll be zooming in and out in time and space, so it will be probably more about why than how in many aspects. Just to jump in right away, federal government is using geospatial data for all kinds of purposes. And we need maps basically to understand the past, to manage the present, and to forecast the future. This is about it. And the Canadian government uses this information for ensuring economic prosperity, social well-being, as well as environmental sustainability. Natural Resources Canada, as an agency, has its own set of priorities defined by the in this case, and the mapping part is very explicitly stated in that red box that Canadians have information to manage their lands and natural resources and are protected from related risks. So we're mandated to produce maps to manage the risks. Geological Survey, which is one of the divisions of natural resources, this is where I work, has the mission to provide geoscience knowledge for competitive mineral and energy industry sectors to ensure environmental stewardship, as well as, again, supply safety and security for Canadians in general. Okay, and we're doing this through by looking at 5 major objectives. So those are unlocking resource potential through geoscience, looking for energy and mineral resources, carrying environmental geoscience work to ensure responsible resource development, so there's no pollution while we're drilling or exploring. Geoscience for public safety and risk reduction, predicting earthquakes, looking at landslides and things alike, as well as following 2 kind of big dreams: Open Geoscience Initiative, open our data to everybody who needs the data because it's paid by taxpayers, and excel in our science and knowledge and people in general. So zooming in, Geological Survey has addressed these priorities through a number of programs. And the programs are highlighted in red are those which explicitly deal with marine or coastal mapping. So geomapping for energy and minerals deals with mapping in the Baffin Bay. UNCLOS is the United Nations Law of the Sea program, which works on extending Canadian shelves. Climate change geoscience program is addressing climate change risks to infrastructure along Canadian Arctic coasts. And public safety geoscience looks at all kinds of submarine hazards. And all these things are achieved through mapping. And of course, mapping involves remote sensing. So in terms of science, 3 major directions of science are marine geological framework science. So looking at offshore bedrock, hydrocarbon resources, crustal research, tectonic processes, and so forth. One big chunk, another big chunk is coastal shelf and deep water studies for more recent geological timescales, quaternary geology, geochemistry, coastal zone. And while doing this, we develop technologies for remote sensing, for optical and physical sampling of the seabed. So seafloor mapping. 2 decades ago or more, Geological Survey of COINAtlantic was one of the first agencies who actually used the multibeam for interpreting structure of the seabed. And we have devised a number of approaches to process not just the speed of response, but also the strength of response, which is the backscatter, and use that for interpretation of the sediment texture. Geological Survey in general existed for a long time, since 1842. It was mandated with mapping Canadian lands. onshore as well as offshore. Now, through this process of ocean mapping, we have established new types of maps, which are called A-series maps. These are 1 to 50,000 scale maps, which present basically a research paper. So this is an example of multibeam bathymetry. I'm talking with an assumption that everybody knows what multibeam is. I don't want to show ships with rays and all this stuff. So this is multibeam bathymetry interpreted by geologists as different geological morphologies with examples of, with instances of examples of moraines and drumlins and so forth, and basically with a research paper on the side, which is peer-reviewed and referenced. So this is not just a map, this is not a data set in GIS, this is actually a knowledge product. Not a data product, knowledge product. So we came up with a series of these knowledge products for marine mapping, which include multibeam bathymetry, multibeam backscatter as a proxy for sediment texture, seafloor geology, interpreted backscatter and multibeam augmented by physical samples, as well as seabed habitat. And habitat is defined here as units of seabed which are similar in their physics, chemistry, and biology, and different from other units in the same way. Okay, that was our actually first definition of what a seabed habitat map is, as opposed to what a habitat means, because any ecologist in the audience knows that habitat is just a place where an animal, plant, or microorganism lives. And how do you capture that place in one map for all the organisms which live there is a big challenge. So actually, that was another breakthrough we had about 15 years ago, defining what a seabed habitat map is. So production processes is relatively easy and understandable. Starts with remote sensing data, both acoustics and seismic, geophysical surveys, geological and optical sampling, and then involvement of the industry who actually cares about our products. And we started with fisheries who are looking for scallops on Browns Bank, and in the process of producing a set of maps for them, we have added $8 million in 1 year to that particular company we worked with. Since then, everybody wanted to produce seabed habitat maps. But it goes beyond just one industry or one fishery. These maps are applied for navigation, for defense and sovereignty purposes, stock assessments, environmental impact assessments, engineering, you name it. Okay. So, getting back to coastal, because I thought I should say something about coastal, the coastal theme of this meeting. My colleagues, Nicole Couture and Gavin Manson, are working on the CanCoast, which is a huge database of properties of Canadian interface between saltwater and land. And they define it in terms of a number of variables, such as tidal range, wave action, geomorphology, texture, and so forth, elevation. And they characterize vulnerability of Canadian coastline to potential impacts of climate change. This little instance here shows the part of Arctic coastline where permafrost is being thawed by changing climate and undercut by ocean, and erodes with increasing speed. The coastal group, and Don Force, by the way, is one of the leaders of this group, is also modeling the effects of climate change and potential impact of flooding on coastal communities and infrastructure. This is an example of what would happen to Tuktoyaktuk if sea level would rise 70 centimeters and a highest observed storm would hit it. So basically most of the settlement would be flooded and the Tuk Island would be breached, which would be a huge hazard for the port. What we do in the coastal group is we actually take repeated RTK profiles of the shore to see how quickly it retreats, and most of the Canadian Mackenzie Beaufort shores are retreating with a rate of about 2 meters per year, maximum rates up to 17 meters per year. And last observation at Tuk Island showed about 10 meters. And with island being about 50 meters wide, you could count really quickly how fast it will go. This is a huge issue for many coastal harbors and ports. So of course, as everybody else, we started using drones. And now the drones allow creation of a digital elevation model with about 1 centimeter resolution in this case, which can be basically surveyed on GIS, and you can establish your coastal profiles extremely quickly with a greater spatial extent. What else is happening there? I'll be using some vignettes basically through this talk. This is just one of the 3 vignettes I want to present. This is the Tech Harbour Multibeam. And what we did, we compared the Multibeam to the available, the most recent at that moment, about 2 years ago, hydrographic chart of the harbor, and we compared the depths as posted on the chart versus the real. And the red dots there show where the actual depth is much shallower than was posted on the chart. So in some places it's 4 meters shallower than the chart says. This is the shipping route into and out of the harbor. So using remote sensing, again using multibeam, we could see the change that happens to the seabed. We can see the drag marks through the harbor. We can see actual keel marks along the shipping channel. And the Northwest Territories Transport Agency is really concerned, and they really want to work with us on that issue, and they need our advice. Going deeper into the Beaufort Sea along the Mackenzie Shelf, which is pretty shallow and goes about 150 kilometers at up to 50 meters water depth, there are a lot of impacts of ice ridges. So these ice covers are ubiquitous there, and they are impacting other side of the things which are of concern to Canadian government. They impact the environment, they impact the Baltic communities, and they change the way they look, and they also define Baltic habitats as a process. So remote sensing is not just showing us what's currently there, it tells us something about the process. It allows us to make predictions, and knowing that the recovery rate for Arctic benthics is about 30 years, we can say that, well, this is a huge issue. Out of our control, though. So, but what's in our control is to understand how the seabed scouring would interact with oil and gas exploration in the Mackenzie Delta. These are all license blocks in the Mackenzie Delta, which is shown here. These are the features which are quite common in the area: pockmarks, mud volcanoes. Some of them are actively sipping, methane. So a lot of slumping on the seabed and so forth. So how do you plan your industry? How do you plan drilling activities?